Well, hello there again. Welcome back, and day 2 of working with the antiderivative. So I know yesterday we had a lot of slides, a lot of examples, and there's going to be a lot of examples again today. I want to give you as many chances to see this worked out first, and then I'm hoping that that helps you be as successful as possible when you when you do the problems on your own. So we're going to work again today with antiderivatives and make the connection to an integral. All right, so we just want to keep summarizing where we've been. We are working with the concept of an integral representing the exactness of area. And we started with estimating, and the estimating comes by doing the geometry, and the geometry is the different rams that we have, and each ram getting a little bit better, and then also the geometry of trap, and then also the geometry of other shapes. But again, those are only so good. There's always a little bit of error, and those are always estimating. So then we move to exact. And we can do exact with Math 9 using the FNInt feature on our calculator. And the final way to do exact is without the calculator, and that's doing the antiderivative. So that's also an exact way of finding the area underneath the curve. So that leads us to the fundamental, which means the most important theorem of calculus. So this works if f is continuous, okay, which means if there's any broken parts, if there's any discontinuity of any kind, this does not work and you can't apply it at all. But if f is continuous, then the integral going from a to b of f of x is evaluated, turns into the antiderivative, so capital F of x plus c. And notice how we put that in brackets. We put a bracket near the beginning and a bracket at the end. Then we put our bounds, and our bounds go on the bottom and on the top of the last bracket. So that's the definition. An integral connects to an antiderivative. Those are equal to each other. The next step is to take the bounds and to drop them into the function. So first you drop in b. So we'll have the antiderivative, and we'll plug b into that, and we'll have plus c. Then we subtract, and you put parentheses, and then we have f, and then we drop the a bound in second, plus c, and then you end your parentheses. Okay, so if you want to be really safe, you put parentheses around the first bit and then minus parentheses around the second bit, but that's the connection. So you find the antiderivative, and then you drop in the values of the bounds and work it out, always starting with the b bound, the higher bound first, and then the lower bound, subtracting the lower bound. So let's practice that. So let's evaluate from 1 to 3 of 3x squared plus 1 using an antiderivative. So we're going to put an equal sign to show that they're equal, and then we put a bracket to show that we've done an antiderivative, and we want to work on the antiderivative of 3x squared. So that would be 3x, and the new power goes up higher. Remember, antiderivatives go up in number, and then we divide by the new power. And then plus, and the antiderivative of 1 is 1x plus c. And then we finish our antiderivative with a little bracket. And then we're going to put our bounds, -1 and 3. So I can reduce here. So I just have x cubed plus x plus c. Okay, then I'll put parentheses, and I'm going to put the number 3 in for x first, and I put it into both parts of the antiderivative. And so that would become 3 cubed plus 3 plus c. And then minus, and then I will put, let's see here, the lower bound in to both places of the antiderivative. So that would give me quantity -1 cubed plus -1 plus c. And then I simplify and evaluate. So this will be 27 plus 3 plus c minus -1 minus 1 plus c. Then I got to distribute this negative. So the whole problem becomes, let's see, 30 plus c, and then distribute the negative, so we get plus 2. It's plus 1 plus 1. And then also distribute to the plus c, so that would be minus c. So I have a plus c and a minus c, so I get 32. So then I'm going to ask you to connect that to the visual representation. So what does that mean? So it means if you drew a picture of this and you had your parabola, and your parabola looks like this, and on the parabola you went from -1 to 3, and you shaded in that area within that parabola, that this whole area would have a value of 32. So it's always good to understand what your number means in terms of a visual. Okay, let's try another one. Evaluate the antiderivative of sine 2x. All right, so we'll put an equal sign, and then we're going to put a bracket to show we're going to use an antiderivative. So let's think about how this goes. Okay, so sine 2x. Let's just remember how the derivative goes. Remember, I've talked about derivatives going in a down direction. So the derivative would be cosine outside first, and I leave the inside alone, and then I multiply by the chain rule of 2. So to do the antiderivative, the outside would be negative cosine, and I leave the inside alone, and then I divide by 2 because I'm doing the opposite when I'm going the antiderivative. So my antiderivative is negative cosine 2x divided by 2. So I'll write that as over 2 plus c, going from pi fourths on the bottom to pi halves on the top. And we're going to plug in parentheses, the pi halves first. So that'll be negative cosine of 2 times pi halves over 2 plus c minus, and then a second set of parentheses, and now I'm going to put in the pi fourths. So minus negative cosine of 2 times pi fourths over 2 plus c. All right, so let's simplify. That's negative cosine on the outside of pi on the inside over 2 plus c. And then this negative sign will get distributed. So I'll have plus cosine of pi halves over 2 minus c. The plus c and the minus c cancel each other out. And then the cosine, negative cosine of pi, that's negative 1 over 2. And then the cosine of pi halves is 0 over 2. So I get positive 1/2. Again, so I want you to connect that to the visual representation. So the graph of this is the sine of 2x okay, and that goes from pi halves to pi fourths to pi halves. And then that means that the area of that archway right there is 1/2. Okay, evaluate the integral from 1 to 4 of 3 to the x dx using an antiderivative. So equal sign, bracket. Again, just use good habits, write an equal sign and then a bracket to announce to the world that you're ready to use an antiderivative. So again, if you need to review 3 to the x, if you do a go down to a derivative, that would be 3 to the x times ln 3 times the chain rule of 1. So if we want to go up to an antiderivative, we would have 3 to the x divided by the natural log of 3 and divided by 1. So this antiderivative would be 3 to the x divided by the natural log of 3 and divided by 1 plus c going from 1 to 4. And then we'll plug in the number 4 in for x. So in parentheses, 3 to the 4th over the natural log of 3 plus c minus the second set of parentheses. Now I'm going to plug in 1 into the same spot. So 3 to the 1st over the natural log of 3 plus c. And then my subtraction gets distributed. Okay, so we have 81 over the natural log of 3 plus c minus 3 over the natural log of 3 minus c. And once again, the plus c and the minus c cancel each other out, giving me 81 minus 3, so that's 78 over the natural log of 3. So connect that to the visual. The graph of an exponential starts out really low and then goes to the number 1 and then shoots up like this. And if we're going 1, 2, 3, 4, and then we have the area bounded up in there, and that area would have a total value of 78 over the natural log of 3. Okay, here's another exponential, e to the half x. So our antiderivative of that would be e to the half x divided by the natural log of e, but also divided by the chain rule, which would be 1/2, plus c, and then from 2 to 7. Now we know the natural log of e is 1. We also know that dividing by a fraction here is awkward. And so it would be better for us to multiply by the reciprocal. So that would be e to the 1/2 of x times the reciprocal, which is 2, plus c going from 2 to 7. All right, parentheses. Let's put in the number 7 first. So that'll be 2e to the half times 7, or 7/2, plus the constant c, minus the second set of parentheses. So we'll put the number 2 in. That would be 2e to the half times 2, which is e to the first, also plus c. Then distribute the negative. So we have 2e to the 7/2 plus c minus 2e to the first minus c. So we're left with 2e to the 7/2 minus 2e. Okay, that does not subtract. Those are not like terms. Okay, e to the 7/2 is a different power than e. You can't subtract things that have different powers. Now we want to connect this to its visual representation. So the graph of e to the half x comes down like this. And then going from 2 to 7, there's 2, 3, 4, 5, 6, 7. So this is a small little area. And that area that's bounded in there would have a value of 2e to the 7/2 minus 2e. So just leave it like that. It doesn't have to be a perfect decimal. You can't subtract it. That would be the answer to that integral. Okay, let's talk about doing this one with an antiderivative. Okay, so I like to do my little work up here. So I can write this as 2x minus 1 to the negative 1. So if I want to go down for that, I would have 2x minus 1 to the negative 2. Oh, I'd move the power to the front, sorry. And then multiply by the chain rule. If I want to go up for this, then the power has to go up. So that would be 2x minus 1 to the 0 divided by the 0, which is where we run into the problems. Okay, so remember when that happens, then we have to look for a different antiderivative, which is going to be the natural log of the absolute value of 2x minus 1. The other thing you have to remember is because we did the times 2 for the chain rule, then when we do the antiderivative, we have to do divided by 2. All right, so my antiderivative here equals bracket natural log absolute value 2x minus 1 divided by 2 plus the constant c going from 4 to 7. All right, let's drop in our bounds. So start with parentheses, we'll have the natural log, and then we'll have 2 times 7 minus 1, that's 13, the whole thing over 2, plus c. Minus, okay, now we'll drop in 4. So I'll have the natural log of 2 times 4 minus 1, that's 7, over 2 plus c. And then we'll distribute the subtraction. So we have the natural log of 13 over 2 plus c minus the natural log of 7 over 2 minus c. And then our answer is the natural log of 13 over 2 minus the natural log of 7 over 2. Now sometimes people do incorrect math after this. They try and subtract the natural logs and say it must be the natural log of 6 over 2. Well, first of all, it's illegal. You can't subtract natural logs. they're not regular numbers, so you can't subtract them. Another thing people try and do is they try and reduce the 6 and the 2 here, and they try and tell me that the answer is the natural log of 3, which is even worse. So, can't do that. Can't do that. Okay, it's just leave it. The natural log of 13 over 2 minus the natural log of 7 over 2. The only thing you could do, okay, I guess, subtraction is the same in natural logs of turning things into fractions. So you could say 13 over 7, I guess, but it's still over 2. But I don't think that's any better. I think you just are better off leaving it as the way it was. Okay, connecting this to the visual. If you graph this graph is called a hyperbola. And this graph would come down in quadrant 1, and it would have a mirror reflection of it in quadrant 3. And then if we go from 4 to 7, there's 4, 5, 6, 7. So we've got this little wedge of area, which connects to the value of the natural log of 13 minus the natural log of 7, both over 2. Okay, this one looks ugly, but this is one of the ugly duckling ones. It looks ugly, but it has a beautifully perfect antiderivative. Okay, this is going to be one of those inverse trig antiderivatives. And it works out to be, because it is the negative, it is a it is the cosecant inverse of x. So it's an ugly duckling. It's got an ugly, ugly equation, which turns into a really nice antiderivative. Plus c from 2 to 2 over rad 3. So let's substitute into our first set of parentheses the inverse cosecant of 2 over rad 3 plus c minus the second set of parentheses, the inverse cosecant of 2 plus c. So we'll distribute the negative. Which will give me the inverse cosecant of 2 over rad 3 plus c minus the inverse cosecant of 2 minus c. So those plus c's and minus c's will cancel out. And now we want to use our unit circle to our advantage. The cosecant of 2 over rad 3 is the same thing as the sine inverse. Now remember, cosecant and sine are reciprocals of each other. So it's the same thing as the sine of rad 3 over 2. And then minus, the next cosecant inverse would be the same thing as the sine inverse, but you need the fraction reciprocal of that, so that would be 1/2. So this is where we use our unit circle. The inverse sine of the rad 3 over 2 is the place on the unit circle, the radian measure, where the y-coordinate is rad 3 over 2. So that's pi thirds. And then sine inverse 1/2 is pi sixths. When you subtract pi thirds minus pi sixths, you get a common denominator. So 2 pi sixths minus pi sixths, which is 1 pi sixth. And again, that represents the area shaded underneath this curve. All right, last example. We've talked about word problems and using the antiderivative to change your units. Okay, and so here we have an example of a decade from the 1970 to 1980 using potatoes, okay, in some country, a particular country, measured in millions of bushels per year. And the question is, how many bushels? So we want to drop off the time. We want to get rid of the per year part. And the only way to do that is to set up an integral to do that. So our integral is going to be the equation 2.2 plus 1.1 to the t dt. Why is it dt? Because we're talking about time. And then what are my bounds? Well, I'm given 1972 to 1975, but I don't do 1972 down here because I only have to measure t as the number of years since the beginning of 1970. So I'm only going to be using the 2, which means the upper bound is 5. Okay, let's do our antiderivative. So equals bracket. Remember, that's the announcing to the person who's grading that this is what you're doing, your intention. 2.2 is a constant. Its antiderivative is simply 2.2t. So those are easy antiderivatives to do. The next one is an exponential. So let's remember how our exponentials go. We take the exponential itself, we divide by the natural log of the constant number, and then also by the chain rule of the power, which was 1 in this case, plus c going from 2 to 5. So now we'll plug in the number 5. So this would be 2.2 times 5 plus 1.1 to the 5th over the ln of 1.1 plus c minus, and then 2.2 times 2 plus 1.1 squared over the natural log of 1.1 plus c. So we'll distribute the subtraction which always results in the plus c's canceling out. So let's see if we can clean this up a little bit. So this plus c is gone. So is this plus c. Okay, so I can maybe get rid of that arrow. Okay, the subtraction is going to turn a couple of the signs around. So I can make this a minus and this a minus. And so then I can just use my calculator, I think, probably to evaluate this. So 2.2 times 5 plus 1.5 over the natural log of 1.1, and then minus 2.2 times 2, and then minus 1.1 squared. So doing all of that on our calculator. And let's see what we get. I get a total of, and I'm going to round here, 21.606. Nope, 608. And then the units on that are straight out millions of bushels. I got rid of the per year part, so it's simply millions of bushels measured. So we used our antiderivative to find out the accumulation of that. All right, so that was lots of examples for you to work on. Finding your antiderivative in brackets first, and then putting each bound, making sure you put your bounds in the right order. All right. I'll look forward to meeting with you on Wednesday morning, and we can work through more of this together. All right. Have a good night.